Hello, my name is Jonathan Peppers, and I'm an engineer at Microsoft. I work on .NET, .NET MAUI, and I want to talk a little bit about how, you know, software development has changed in the world of AI. So this is a project I did kind of on a weekend and really just one Saturday, I would say. And I was only half paying attention to what I was doing. So I thought this would be, there's a lot of people who maybe haven't tried AI. Maybe they tried it 6 months ago and it was bad. And I'm just here to say that like things have changed, right? So, but let's get into it and we'll see if this, changes your mind about some things. Um, so why would I even do this? I was saying a little bit, but uh, all developers need to have their Opus moment. So if you haven't used Opus 4.5 or 4.6 or 4.7, um, and using it in whatever tool you want is fine, but it can write some good code, and this talk will kind of show some of that. So at Microsoft, I have access to a lot of tokens. So there might be some things I can do here now that all developers will be able to do in a few months. Um, but I'll show the tools I used. And just to say, like in my day-to-day work, I don't use an IDE anymore. For like almost 20 years, I use Visual Studio. Maybe in the past couple years, I've switched to VS Code more. Um, but now I'm at the point where I just kind of use an AI chat session, and then I review AI's output of the code, and I can actually get a lot done faster with that workflow. And a lot of my coworkers are doing the exact same thing, right? And this is not just a Microsoft thing. I mean, I've heard of this happening at Google, other big tech. Um, but let's get into what I did here. So this was my thought of the to like prove that AI can solve hard problems. In my mind, I thought, oh, let's go find a recent CS paper from a college, like some university discovered this new algorithm. I give the paper to AI. I say, code this in C#.NET, and then let's find out if this algorithm is actually faster than the built-in algorithms that are already in .NET, right? Um, and the question is, can AI help me do this faster than I would have been? Like, is AI giving me a superpower here, right? I mean, I was trying to not fully understand the paper and just start with, hey, here's a paper, right? And that's definitely what I did. And I learned more about the algorithm after the fact. So this is not, this has been done in the past. If you've heard of the book Masters of Doom, talks about John Carmack, and he had a problem in the game Doom where he needed to basically do pathfinding for the game. You imagine you're a guy and you have enemies, and you need to do collisions. At the time he was having trouble getting the hardware to do what he wanted the game to do, and so he found a paper called BSP, binary space partitioning trees, and he implemented the paper, right? And so when he did this, it made the game fast enough that where he could make the game what he wanted, in short. But check out this book if you've not read it. I've just loosely heard of it. I've read another one of a book related that talks about Wolfenstein 3D, but I think this one is also really good to read if you have not. So here's what I use. Here are the tools that I use to do this. Um, I used all of these. You can use any, pick and choose what you want. You could also have used Claude CLI here. I happen to use GitHub Copilot, one, because I work at Microsoft, and then it actually has a model selection tool where if down the road a different company other than Anthropic and Claude has a model that's really good, I could use it. Um, and that's one benefit of using Copilot instead of Claude. Um, Claude CLI, of course, is a little different, but Copilot CLI is basically the same thing. Um, so all the different products I use, there's Copilot and VS Code. There's the CLI. Those kind of do the same thing. The Copilot code review is on GitHub, and so when I would ask the AI to open a pull request, I would have another AI that would review the code. And I think this is just useful in general to turn on any project on GitHub. But check that out. And then GitHub also has a feature where you can file an issue and assign Copilot. This is similar to the CLI, except it's a cloud session. And I used that for times when it was an easy task and I didn't want to think about it, and I could just kick it off and review what came out at the end later. But I used all these together to do this project. So let's talk about the paper I found. So there was a paper that found a new sorting algorithm. It's a sorting network, which we'll talk what that is, but the concept is you have an array that is either 27 length or 28 length. And this is a magical sauce to sort these things faster than any other traditional algorithm. But it is tied to how long the array is, right? So this is more specialized than a general purpose sorting, right? And this paper came out in November 2025, so it is somewhat recent. So let's talk about the sorting network. Here's an example of just general concept, is that you have if statements that check if each item in the array is larger than the other, and you swap them, right? And so you can imagine flying down through these if statements, and you swap the positions, and then at the bottom, the array is sorted, right? So there's some reasons why this is faster. It can be hardware optimized for hardware. I'll show you how that works. And it can do it in fewer steps than like some traditional sort algorithm, right? So let's look at more examples. So let's imagine you had an array of 3. You can imagine having a method that has just 3 parameters, right? In our example, you'll pass in an array, but just imagine it's the 3 parameters passed in. And you basically have 3 if statements, and you would run this code, and then at the end, they would be sorted, right? This is the basics of what a sorting network is. These 3 if statements, right? Now imagine taking this to, it's not just 3 lengths, but 27 and 28. The paper actually has done their own research to figure out the minimum number of if statements they can do, which I believe is that maybe they went down from 14 to 13 to sort a 27 or 28 length array, right? All right, so here's what an initial implementation looked like. So I gave the AI the paper. It spit out something like this. It knew off the bat to use the new unsafe APIs in C# that for speed, right? So we're skipping array bounds checking and things like that. But these tricks are the same thing that .NET Runtime and the BCL already use, right? And so you can imagine, just like the if statements before, you have like 14 of them, and then at the bottom, the whole thing is sorted. And there are a lot of local variables. You notice that the E1 through E26, and then at the end, you write the sorted values back. Right. So the first attempt, the AI wrote a generic approach. So instead of like int, right, it used a t, right, and it tried to generalize the entire thing. And it ended up being slower than the BCL with this approach, which makes sense. The BCL actually is optimized for integer arrays and a couple others I'll show later. Um, but the things that went wrong is that when you're generic and you're using a T, you end up using interfaces like iComparable T, um, and then the generic constraints in general are just slower than if you like had the concrete type there, right? Um, so I kept digging. I was like, the AI at this point, the AI had created an algorithm that works. I had unit tests that compared the new code versus just general array.sort, and I was getting the same answer out. So I had something that was working. It just was not actually faster yet, right? So then I started looking at hardware intrinsics. So um, what this is a feature in .NET. I think it's been around for several .NET versions, and they keep adding more and more of these. But what it lets you do is they have APIs that they're not really methods. They like teach the JIT or AOT compilers, hey, these turn this code into these specialized instructions that can run on a certain processor, and takes advantage of like more complicated processor instructions, right? Um, so you think about our if statements, our 13 or 14 if statements. What if you packed all of those numbers into a single vector 256? You called shuffle so that it would have their positions. Their positions are in the vector in a known order, right? And then you can compare all of the values in one instruction. So vector 256 min and max. It lets you basically run all several if statements in one as if they were packed into a single 256 uh, bit vector, right? And so it's not in parallel. It's, hey, I'm running all these if statements in one CPU instruction or two CPU instructions, where the other code would have been several CPU instructions. Um, and then at the end, you can get the value out with conditional select. So hopefully, hopefully that is a decent explanation of what's happening here. But the key insight is I didn't write this code. I told the AI, make this code use hardware intrinsics, and so it can be as fast as possible, right? And I wasn't telling it how to implement it. I said, look at .NET Runtime's code, see what they're doing. Now, let's use vectors. Um, so before I mentioned that things were slower. The way I knew that is that I had created a BenchmarkDotNet project. Um, and so I had a benchmark for every primitive type in .NET. So like byte, sbyte, short, int, long, all of them, string, um, and actually could run the benchmarks on my machine and see which is faster, the BCL or this new code, right? And benchmark.net's really good because it does the statistics for you. It runs operations over and over and over and like writes out your CPU information in the log. Like it does all these things to like verify that the AI isn't making things up, right? That was the whole point of the benchmarks, right? Um, and then so this is how I knew that the original code was slower. Um, but once I have these benchmarks in place, I know if it's faster or slower. Um, I could also run them on GitHub Actions. So AI also wrote the YAML for this, but so I would have a pipeline that would build, and then a pipeline that would fan out to every OS and architecture that was free. So I could do macOS ARM64, Linux ARM64, Linux x64, and Windows x64. And so it fans out on those four machines, runs the benchmarks, and saves the results. So I could see not only were things faster on my machine, or they faster in the cloud on GitHub Actions, right? And then at the end, it kind of summarizes all the numbers and puts them on the build summary, right? So this is an example of like what I was seeing on my machine. I did this on an older computer I have upstairs, but I have an Intel Core i9 Windows machine. This is actually, it says x86, but it it says that because the intrinsics were x86. But anyway, the speed up I saw with the final algorithm, the vectorized hardware intrinsics code that the AI spit out, a byte array was actually 33 times faster than the BCL. And then we got the whole list down here. And come to find out that the BCL was actually already very optimized for int, char, and ulong, where they already have hardware intrinsic code paths in the BCL, right? So on a lot of array types, this was a lot faster. And then it was just a little faster on the ones the BCL is already pretty fast at. So here's the same numbers kind of in graph form showing the ones with big green bars are really fast, and the little gray bars are very comparable or just a little faster. I think car what ended up being like 10% faster. So there is something in there which makes sense because of string sorting is why I think the BCL would have that be so fast. And so on a Mac Apple M1, this was actually running in GitHub Actions. You have a similar results, 41 times faster on byte. And then here's the second view. I think there were some cases, almost everything was faster, but there are a couple benchmarks where the BCL was faster, like a reverse sorted int array. The BCL was just slightly faster. And at that point, some of the numbers I have were kind of within noise. So it might be that they were actually just very same or the similar. So that was good. Right. So I guess the conclusion to this, if I did this myself with no AI, I could have spent a week doing all this, right? I think what is interesting is that I could take this and shorten the development time to half paying attention on a Saturday to make something compared to like me, if I did it all myself, I wouldn't have even done this project, right? Like it's just been, oh, that's too much work, you know. Copilot did all the tedious stuff, like it generated the benchmarks, the unit tests, the build pipelines. And me as a human, I ran all these things to verify the AI is correct. Because of course it's gonna, and well, just like a human, it would try to do something that would make it faster, and then we would run the benchmarks and it wouldn't be faster, and it would iterate, right? Just like a human would. And what helped is the human in the middle making sure that the AIs aren't making things up, basically, right? And I mean, if this is freaking you out, I do think that the like domain knowledge still matters. Like I still told the AI what to do. I knew the features in .NET that needed to be used and told the AI to go use them, right? I knew about BenchmarkDotNet. I knew, all of these, I don't know, good software practices still apply to what I did here. And then just, the results of this kind of speak for themselves. Go check out the my GitHub repo on this. I may turn it into a NuGet package. I think it needs a little more like design thought to it, and I'll say why. But thanks for watching. If a question might be is like, hey, go put this in .NET, right? There always is going to be a more specialized algorithm that you can apply to your data than what a general algorithm can do. So I would need to generate a sorting network that would work for every array size. And what that would do, that would be a lot of code. And so what would happen is either the JIT would have to compile all that code, or AOT compiler would compile all that code, and both of them would increase sizes of things, right? Sizes of code, either on disk or in memory. Um, so I think what could be done, this seems good, is if I could make a source generator where you decorate some type with an attribute and you say, hey, optimize this thing for arrays of size 16, 32, whatever, and it would generate a sorting network for you. And then you could use that sorter object on a specific array of a certain size. Um, that actually feels like a useful thing, but it feels like a thing that should be in a NuGet package to me. So at least for now. But yeah, check out the repo, check out the paper, comment if you think I made something up. Please educate me, because anyway, thank you. Bye.